Okay, so listen, I have another data set here. Again, I'm going to make this very small, right? 5 items. I also want to remind people that anything that we do, any of the procedures that we're doing here, um, we can do the same exact procedures if instead of 5 numbers we had 50 numbers, or instead of 50 we had 1,563 numbers, right? The computations you just keep doing the same thing. So I do want people to understand that everything we're doing, we can do with larger data sets. And most of the time you're going to do this on a computer anyway. I will show you how to do that later, but it's good to get practice at math, I think. That's just my personal opinion. So let's get our mean and our sum of squares for this group of numbers. But before you start doing the computations, I would ask you to look at these numbers and make a guess about what the mean is for these numbers. Please make a guess. I know that my colleague Dr. Emmons in the math department does this with his students too, because making guesses gives you an indication of how much you understand or might know the material. If I looked at this group of numbers and my guess for the mean was 23, well, then somebody would know that I'm completely clueless. If I looked at these numbers and I said, well, I think the mean is 237, well, I'm totally clueless, okay? Now, those are extreme examples. If I looked at these numbers and I said the mean was 130, that would also be kind of a weird guess, right? The mean is going to balance this distribution. So, I'm going to make a guess. I have not calculated the mean here yet. I'm going to make a guess. It's going to be 152. Okay? That's going to be my guess. I don't know. So let's do the computations. I mean, we're going to get the value, but let's see how close I was. Divide by 5 in this case, and the average is 145. Well, I was wrong. Of course, that's okay. But 152, 145, not that far off, right? Let me just double check, make sure. I'm always going to double check my answers. And by the way, if you think that you can't make a mistake just because you're on a computer, you're sadly mistaken, because I've seen it often because people will plug in the wrong number. So here's our mean, 145. Okay, I'm looking at this, I'm like, well, that does make a little bit more sense rather than my 152. That's okay. I'm not brokenhearted about it, okay? Let's do our sum of squares, and we're going to use the computational formula, okay? So here it is. So we're going to square each of the numbers and add them together. 135 squared is 18,225. Okay. 150 squared is 22,500. All right. 161 squared. This is why it's good not to have a large data set when we're doing this by hand, right? And then finally 137 squared is 18,769. Okay, so let's add these together. 18,225 plus 22500 plus 25,921 plus 2164 plus 18,769. Okay, 105,579. Okay, and to get the total for the x, I could multiply this by 5, right? I'm not going to go through and add all those up again. Multiply this by 5, which would give me 725 squared. So we have 105,579 minus, let's do 725 squared divided by 5 is 105. 125. Okay. My sum of squares then, 105, 579 minus 105, 125. 454. I'm going to put my zeros in there for my final answer. Okay. 454.00. Sum of squares is a measure of variability, but we left off with the last video wondering what that means. How does this number sort of fit in with these? Well, we're going to do a little bit of more manipulation here. So this was, let's put this in words, my sum of squared deviations. Okay, my sum of squared deviations. Now let me ask you this question. Well, let me go back. So we're going to take each of the deviations, right, x minus mu. We're going to square that, which of course tends to make those numbers get big really quickly. Then we're going to add all those up, however many scores are in our data set. Sum of squares gets large very quickly, okay? Tends to. Let me ask you this question. This is a thought question. Suppose that instead of, the next time you take an exam in a class, instead of the professor telling you what the average score was on the exam for the class, suppose the professor reported the total number of points accumulated for the entire class. Everybody with me? Instead of the professor coming in and saying, the average on the exam was a 71, suppose the professor said, the total number of points, that is the sum of all your exam scores, was 3,427. Would that tell you how well the class did? Now, before you say no, please think this through. It's not common, right? That's not what I'm asking. I'm saying, does that tell you how well the class did? Some of you may still say, no, not really. And I'm like, well, does reporting the average tell you how well the class did? And most of you say yes. And I'm like, an average of 71 doesn't tell you how you did, doesn't tell you how any other specific person did. And in fact, we've already talked about the problems with the mean. We have to be careful. The sum of all the exam scores tells you just as much, because if I said the sum was 3,267, and then in the next class I say the sum of all your scores was 4,027, then you did better on the second exam, right? You would get that same kind of information from the average. So the sum of all the test scores actually tells you how well the class did, just like the average does. And then you have to say, well, why do we use the average? Why do we use the average? There's a very, very good reason why we use the average to report how the class did. But I'm wondering if anyone knows this offhand, my class. Well, here's the biggest benefit of reporting the average, is it because it adjusts for different sample sizes. For example, if we had a class of 100 students and I was using the sum of the scores, and I wanted to compare that to a class of 20 students and I was using the sum of the scores, it's not likely that the class of 20 would ever be better than the class of 100 even if that class did more poorly, because you're adding up all the points. This is why averages are used for a lot of things, because it adjusts for different sizes of groups. So I can get the average for 100 students, and I can get the average for 20 students, and I can compare those. Comparing the sums doesn't work unless you have exactly the same size class. And even within a single class, you know, sometimes people drop out, sometimes people add, and so on and so forth. So doing the sum is not the best way to do it. Well, we're going to do sort of the same thing here for our sum of squares. We just have to think, you know, this is where things are getting more complex, right? This is the sum of the squared deviations. How would I get the average squared deviations? Okay, or the average squared deviation. If I have the sum of your test scores, how do I get the average of the test scores? Well, I divide by n, right? I could get the addition of everybody's age, or I could get the average of your age, and it just involves one more step, and that is we're going to divide by n. Whenever you divide by n, you get an average, okay? You divide by n, you get an average. So here's what we're going to do. We're going to do, we're going to divide by n here. Now, instead of, right, sum of squares is the sum of the squared deviation scores. If we divide by n, then how would we describe this in words? Well, then this becomes the average squared deviation, right? Take my sum, I divide it by n, so now it becomes the average squared deviation. Everybody got that? To get an average, divide by the number of things that went into that sum. Well, look at this. Sum of squared deviations, average squared deviation. It's like, you know what I'm going to do now? Remember why we squared? Remember why we squared? I hope you remember. And that is because we wanted to get rid of the negative deviations so that negative deviations and positive deviations didn't just balance and give us a 0. Okay? If we didn't square, every time we would get the sum of the deviations to be 0. That's what balancing the deviations mean. We're going to take the average square deviation, and we're finally going to undo the square. If you recall from a previous video, we talked about a deviation score of -10 and a deviation score of +10. We said that those were equally deviant from the mean. It's just that one was below and one was above. So we squared it, right? Now we can consider those two equal because we square. Well, now we're going to undo it, the square. This becomes 10, this becomes 10. You see, it's a little bit of mathematical calisthenics here. So we did squaring for a reason, for a very good reason, hint, hint. But now we're going to unsquare this. And the way we're going to do it is we'll take the square root. Okay? So then this becomes, we went from sum of square deviations to average square deviation. Take the square root. So now this becomes what? The average deviation. Okay? And in fact, it's an extremely important video today because average deviation, and I don't know where this started. I suppose I could look it up in the history of stats or something like that. But we have a special name for this, and it's called the standard deviation. Okay. The standard deviation. And it has a symbol like this. Okay. it is a lowercase sigma, okay? It's a lowercase sigma. And so this value we get taking sum of squares divided by n, take the square root. And this is how it works. We started with our sum of squares. Sum of squares. If we divide by n, we get the average square deviation. I'm going to undo the square. This gives us average deviation. Standard deviation is the average deviation. And here's the concept. It is the average amount that scores deviate from the mean. It's the average amount that scores deviate from the mean. Just like the average on an exam would be the average score that people got, right? This is a derivative of that in a way. It's the average amount that scores deviate from the mean. As a group, okay, we're not talking about an individual person. That would just be x minus mu. We're not just talking about x minus mu. This is taking all of the deviations and saying, well, on average, how much do scores deviate from the mean? On average, how much do scores deviate from the mean? Okay? And I'm going to ask you to make another guess. I'm going to ask you to make another guess before we do the computations, folks. Please, before we do the computations, make a guess. Here's the average for this group of scores. The average is 145. I want you to make a guess about what the average deviation is. What's the average deviation? I want you to make a guess. Please guess, okay? So if the average is 145, and I'm looking at this, how much on average do scores deviate from 145? How much on average do scores deviate from 145? I mean, I don't know, 8? Maybe 6.2? 4.8? I don't know, maybe 7.5? On average, how much do scores deviate? How much do these scores deviate from 145? These are good guesses, I think. If you made a guess of 37, then I would know that you really don't know what I'm talking about, okay? If you said that this is the average score and these vary by about 1 point from there, if you said that, I would think that you're not really getting it. You see, this is what guessing does for a teacher. What guessing does for students is gets them thinking about the concept. Here's the mean for this group of 5 scores. I want to know, on average, how much do these scores deviate from this? Now, we can certainly do the computations. Listen, you're all intelligent college students. I'm assuming with practice, you can do the computations very easily, okay? What I'm asking you to do is think about the concept. When you get your computer printout, you'll have the answers. If you don't know what it means, you're going to be lost, okay? So, well, we have our sum of squares here. So in this case, we can actually, let's do this. Let's calculate the value, okay? Let's calculate the value. Sigma, our standard deviation, is equal to the square root of sum of squared divided by n, okay? So in this case, we have 454 is our sum of squares, divided by 5. Don't forget to take the square root. That's the most common mistake I see on exams, is people will do this, but they forget to take the square root, okay? So I'm going to do that value. This is 454 divided by 5. So this is square root of 90.80, okay? And I hope that you have some knowledge of squares and square roots. I know that the square root of 81 is 9, okay? I know that the square root of 81 is 9. If you don't know your squares and square roots, for 1 to 10, you're at a disadvantage. Oh well. I mean, this is the problem. People don't want to learn math, and then they find that they're at a disadvantage. And I'm like, well, stop, ignoring learning math is my advice. So I know this is going to be 9 point something. And of course, square root of 100 is 10. Square root of square root of 81 is 9. I'm still going to do my, use my calculator. I don't know this value, but I certainly know that it's going to be 9 something. That will help me, because if I get an answer, if I get 27, I know I made a mistake. If I get 1.4, I know I made a mistake. So I plug this into my calculator, 9.53. Okay. 9.53 is the average deviation for this group of scores. 9.53 is the standard deviation. It's the average deviation for this group of scores. Okay? My first guess was actually the best guess. This wasn't bad. These are still in the ballpark, right? But what I'm going to do then is I'm going to report my standard deviation. And in fact, sum of squares is usually not what people will report. This is an intermediate step. What people typically will report is the standard deviation. And very, very important, another very important video, this brings our measure of variability sort of into the ballpark, right? Because it does relate, or you should see it as relating to this group of numbers. Not only can you make a guess about the mean, because you're familiar with what the mean means, right, the average, but I'm expecting that you'll be able to make a guess. Yes, a guess about the standard deviation. I'm also expecting that you should be able to calculate it. Okay? This says the mean is 145, and if we have a nice normal curve, this should be a measure of central tendency. Okay? This is a measure of variability. This is a measure of central tendency, the mean. This is a measure of variability, standard deviation. Now, sum of squares was a measure of variability as well. But that number gets really large, really fast. We're taking sums, and so I can't compare two groups that are different sample sizes, right? It would be very difficult to compare those. This takes into account the different sample sizes. We'll tell you the average amount that the scores deviate from the mean. Okay? That's what standard deviation is. In order to compute standard deviation, we have to get sum of squares. Dividing by n gives us our average. And then finally, we're going to take the square root. That gets rid of that step that we had to do to get rid of the negative. Okay? Now, the book talks about variance, which is that value, and sometimes they'll do this. If we don't take the square root, then this is sigma squared, standard deviation squared. I am not that concerned about variance at this point. Okay, we may get into it later in the semester, but typically we're going to go from sum of squares to standard deviation, because people do understand this. Now you do, and you're becoming more sophisticated as a professional. You know what standard deviation is. Standard deviation is the average deviation. It's on average, how much do scores deviate from the mean. Okay, that's how it works. All right, let's do one more before we move on, and I hope that you're feeling more comfortable, and I hope that this is not too redundant. Where are we at? I. Let's do. Let's see. Let's just make up some. Well, let's do this. We'll make it a little bit easier for ourselves this time. Okay. So what would be your guess for the mean for this group? I mean, I don't know. My guess would be probably going to be something like 7.5. I don't know. That would be my guess. Let's see what the actual mean is. You see how this works? We make a guess. We do, we get the details. 14 plus 20 plus 12 plus 9. See how I did that? I can add these two numbers and go through. Saves me a little bit of time. 55 divided by 7, 7.86. Oh, I was pretty close. Okay, not bad. Now I'm going to ask you to guess what the standard deviation would be. Here's the mean. What would the standard deviation be for this group of scores? What would be your guess? I mean, my guess is going to be something like maybe 3.25, right, for sigma. Maybe 2.87. Maybe, I don't know, something like that, right? I'm assuming that you sort of get it. And if you're making guesses like this, then that gives me some hope that you are getting the concept. And when I say guess, I don't mean random guess, right? What does sigma tell us? It tells us, on average, how much are these scores varying from this? Okay. Well, let's get it. So I want to get sigma. Here's how I calculate it. Okay. I already have that number. That's 7. But I need my sum of squares. So the first part, and because I know my squares from 1 to 10, 1 to 12, makes it easier. 16, this is 4 squared is 16, this is 100, this is 64, this is 144, this is 49. I mean, you can get this with your calculator, but it's nice to know that stuff. Yep, I'm annoying. So 116 plus 64 plus 144 plus 49 plus 25 plus 81 equals 479 minus 55 squared divided by 7. 1, 2, 3, 4, 5, 6, 7. I'm going to be very careful. Is 432.14. Okay. My sum of squares is equal to 479 minus 432.14. 46.86. Okay. Once again, even though this isn't as huge as the other ones were, because we kept the numbers manageable, okay, it's still, we still have that same problem. Like, how does this relate to these numbers? Well, let's do the rest of this here. So this is square root 46.86 divided by 7. Take the square root. 2.59 is my standard deviation. Look at this. Pretty good guesses. I was a little bit, higher than I should have been. That's okay. These are reasonable guesses. If I asked you to make a guess and you made these guesses, I'd be like, awesome. If you said 14, or if you said 43, or if you said 1, I would be like, not so awesome. Okay? So standard deviation here is 2.59. Okay? And so that is standard deviation, and it's a measure of variability. Sum of squares is a measure of variability, but it ends up giving us I mean, we can compare different groups of the same size, but we really need to do this step to sort of make it manageable as descriptive statistics. Okay, so let's see. I think that we're going to end this video, and hopefully, if you you did the computations and got this answer, if you're having trouble, make sure that you contact me, and I can answer questions about that. Because then the next video we'll talk about variability in general. This is the gold standard for variability. This is the gold standard for central tendency. But of course, we have the median and the mode that go into that category of central tendency. We know that you can use those for different reasons. I'll talk about one more measure of variability that we can use in place of standard deviation if need be. Okay, so we will pick up from there in the next video.